In this video, we're going to discuss some important definitions and properties of modular arithmetic. Modular division, which we write as m mod n, is the remainder when m is divided by n. So we take m, we divide it by n, and what we're going to get when we do this is some number that we call the quotient and some remainder. Now this remainder number has to be less than n. It also has to be bigger than 0. It could equal 0, but it can't equal n. If it does equal n, that means that we could have made one more division and q would be bigger by 1 and so on and so forth. Hence, our possible values for outcomes when we do this are the integers from 0 until n minus 1. I also want to make an important note here that all values that I'm going to talk about in this video refer to integers. So when I say a number, I'm actually referring strictly to an integer for this video. An equivalent way of writing this is to say that m mod n, which is also known as modulo, is equal to r, where r is this remainder. It's this extra little piece that we add to n times some quotient, and when we do that, our sum is m, which came from right there. And if you notice, q doesn't play a role in our statement m mod n is equal to r. Q is kind of our hidden value in there. So for a moment, we're going to look at numbers modulo 3. This means that our possible outcomes are going to be 0, 1, and 2. So notice, if I take 0 modulo 3, I get that 3 times 0 plus 0 equals 0, but it's this 0 that allows me to say it equals 0. In fact, this is a statement. 0 mod n is going to equal 0 for any value of n that's an integer. But let's go back to modulo 3. So 1 mod 3 is going to equal 1. Because when I take 3 and I divide it into 1, it won't go in a full time. So when I subtract, I'm left with a remainder of 1, which is where that comes from. And the sentence that I can write is that 3 times 0 plus 1 is equal to 1. The same thing's going to happen when I do 2 mod 3. It's going to equal 2. My sentence is 3 times 0 plus 2 equals 2. And it's this 2 right here that leads me to be able to make that statement. But then something interesting happens. If I look at 3 mod 3, well, if I take 3, I divide it into 3, I get 1, and I have a remainder of 0. And my sentence is 3 times 1 plus 0 is equal to 3. Again, this 0 is the same as that other one. So I now have two numbers where when I look at them with regard to modulo 3, I have an answer of 0. And in fact, this pattern is going to continue. 4 mod 3 will equal 1, and 5 mod 3 will equal 2. So I want you to notice some things. Mainly what I want you to notice is that 2 and 5 give the same answer when we look at them with regards to modulo 3. And the difference between 5 minus 2 is 3. This is all very interesting and actually leads us to be able to define equivalence with regard to modular division. Essentially what we can say is that if we have two numbers, like the ones we just saw, where we had 2 mod 3 is equal to 2, and we had 5 mod 3 is equal to 2, then we can say that 5 is congruent or equivalent to, however you want to say that, to 2 modulo 3. The other thing you should notice is that when I take the difference between these two numbers, 5 minus 2, that gives me 3. What about another number? Let's look at 14. 14 mod 3. I take 14, divide it by 3. It goes in 4 times. I'm left with a remainder of 2. So 14 can be written as 3 times 4 plus 2 is equal to 14. This 2 is the same as that 2. Gives us our answer. So we also know that 14 minus 5 is equal to 9. And 14 minus 2 is equal to 12. And we can also say that 14 is congruent to 2 mod 3. So when the difference of these guys is divisible by our modulo number, then you know you have an equivalence class. The next definition that I want to talk to you about is greatest common factor. I write this as GCF of, we'll say, m and n, two integers. This is the greatest factor that the two integers share. So let's look at two numbers. We're going to look at the greatest common factor of 5 and 125. I find it helpful to write each number in terms of its prime factorization. 5 is already prime, and 125 is actually equal to 5 cubed. So the largest factor that they have in common is 5. So we say that their greatest common factor is 5. What if we looked at the greatest common factor of 9 and 41? We write 9 as 3 squared. 41 is actually prime. Notice I can't break 41 down into any more pieces, and 41 clearly isn't present in 9, and there's no 3's present in 41. In this case, we say that their greatest common factor is 1. Though we don't write 1 when we write prime factorizations, we still know that it's present. In fact, this is a very important case. If the greatest common factor of two integers is 1, we say that these numbers are relatively prime. It means that the only factors that they share are 1. When you write the prime factorization of the two numbers, they have nothing in common other than the presence of 1, because we can multiply any number by 1 and get it back. Knowing that two numbers are relatively prime is very important when we're talking about modular arithmetic. If you remember in class, we talked about how when we're in the class of modulo 26, I told you that 7 and 15 were inverses. This essentially means that they undo one another within regards to modulo 26. What you should note is that the greatest common factor between 7 and 26 is 1, and the greatest common factor between 15 and 26 is also 1. This is important because when we look at the definition for how to determine if a number has an inverse with regards to the modulo of another number, we need to first see where we have relatively prime numbers. What we know is that this happens if the product of two integers, we're going to call them a and b, if this product is equivalent to 1 modulo n. So let's look at this. 7 times 15 is equal to 105. 105 mod 26. If I take 105, 26, it's going to go in 4 times, which is 104. So I have a remainder of 1. If we look then at 105 and divide it by 7, we get 15. Therefore, this connection, also taken into account that their product is equivalent to 1 with regard to our modulo, lets us know that they are inverses of one another. Let's see if we can find the inverses with regard to modulo 5 for the numbers that are in that set. So our possible outcomes, looking at modulo 5, are 0, 1, 2, 3, and 4. So notice that 5 is prime. So because 5 is prime, we know that 1, 2, 3, and 4 will have inverses because they're all relatively prime to 5. So let's see if we can find them. The first thing we need to look at are multiples of 5 plus 1. So 5 times 1 plus 1 is 6. 5 times 2 plus 1 is 11. 5 times 3 plus 1 is 16. 5 times 4 plus 1 is 21, and maybe that'll be high enough for us to look. Remember that we're looking for numbers that have a remainder of 1, and all of these will because I have added 1 to a multiple of 5. Now let's look. I'm going to start with 2 and see what happens. It looks like 6 divisible by 2 is equal to 3. This means 2 and 3 are inverses. $16 divided by 4 is going to be 4, so 4 is its own inverse. And if we started with 5 times 0 plus 1 is 1, 1 divided by 1 is 1, then 1 is also its own inverse. So this is the end of the first video where I cleared up some definitions for modular arithmetic. Please come and see me in my office hours. I'm generally around times other than this, so send me an email just to make sure I haven't stepped out to go warm up my lunch or something. But I'm in my office here, Monday, Wednesday, Friday, from 11 to 12. My office is in Founders North 2.208, and you can send me an email if you have any questions about what's in this video.